two problems together. In some tutorial classes, I'll ask you to solve yourself, and some classes I'll help you. But 1 hour we'll devote exclusively for the solving tutorial problems. So that is the way we'll proceed. In today's class, I'll teach you something like the linearization and how to get the linearized equation of motion, which is very simple thing, but one has to know. Okay, so last class we were discussing different types of vibrating systems. Okay. One classification was based on linearity and nonlinearity. So linear system means that, okay, let me ask you, when do you say the system is linear? When do you say the system is linear? Any answer?
When the equation of motion is linear.
Equation, that is fine. Equation of motion actually is derived from the model, but the system is a physical system. So equation of motion, definitely if the system is linear, only then the the equation of motion will be linear. Fine. But it is not vice versa. That is when the equation of motion is linear, the system is linear. It is not so. System comes first, then comes the equation of motion. The equations of motions are derived from the model of the physical system. So we have to know what do we mean by the system being linear. So linearity has a property that there the superposition principle holds. Means what? Suppose I have a system and I give input to this system. Okay, so there is there are certain provisions for applying forces or displacement excitation. Now superposition says that if the response is found individually for each of the input, then the response will be the sum of all the individual response when the excitations are applied together. Okay, so that is one test we can do. Suppose we have a system where we have two inputs. Okay, let us say I denote this by F1 and F2, two different forces, okay, applied on the system. Now with F1, if you get the response, that is, if you get the response as X1 when you apply the force F1, let us say, okay, and X2 is the response when you apply the force F2. Then when we apply F1 and F2 together, then the response will be X1 plus X2 with the same initial conditions, of course. So this is what the significance of the linearity of the system. So the system is linear. So naturally, if you so a consequence of this is that if you double the excitation, that means if you increase the force 2 times, then the response will be also increased 2 times, twofold. Okay, so that will happen only if the system is linear. And in the equation of motion, of course, the linearity will be reflected. The equation of motion will be also such that the equation becomes actually a linear differential equation. Okay, linear differential equation of any order, but it will be linear differential equation. Okay, so this is the difference between linear system and non-linear system. The superposition does not hold good. So physically, if you want to verify that whether the superposition holds good or not, then what you can do, you apply a force, you get the response, you double the force. If the response gets duplicated, the double, then we can at least do fair approximation, because you have not tested for all the forces. So with your testing, you can say that the system is a linear system. Okay. So for example, the pendulum which we have taken earlier, if you give a small displacement, then the response you can get. And if you give a small excitation to the bob, then you get the response. As long as the motion is small, that is within, let us say, 4 degrees from the equilibrium position, that is a vertical line, then the motion is actually nearly a linear motion. But if theta increases beyond certain value, then the equation of motion becomes non-linear. Okay, I'll just come here. I'll just stop here for a moment. Just 5 minutes. Give me some 5 minutes time. There is some person who has come. I'll have to just meet him. Just a second, please. Okay, so that is what we will see today, how to get the linearized equation. But before we go to that subject, let me complete what we had started in the last class. The systems were broadly classified into 2 parts: linear system, non-linear system. And also, depending upon the excitation, there were different types of excitation. One was the force excitation, that is the applied excitation is in the form of force. There may be displacement excitation. That means the displacement is given, so we control the displacement of one or few points there. And for controlling, we definitely need to apply force. But this force does not appear in the equation of motion. In order to get the amount of the force which is required to give this controlled excitation, you need to add another degrees of freedom, which I explained with the help of one example. That is the base mass I did not take for the first time, but the second time when I took, then it gave us the force which was required to sustain the oscillation. Okay. The third kind of excitation which we talked about is the parametric excitation. What does it mean? There, the excitation is appearing in the parameter. So parameter means that in a physical system there are certain quantities which can be kept fixed. For example, the mass of the system, stiffness of the system. But if we, certain means, if we can change those fixed parameters, so they are no more fixed, so they can change. And the parameters, if they are changed in the particular fashion, then the excitation, so this amounts to giving certain excitation. So the system can actually start oscillating because of this kind of changing of the fixed parameters of the otherwise fixed parameters of the system. So here this particular excitation is called parametric excitation. There is another kind of excitation which I need not explain to you in details, but I'll just tell you that suppose we have, let us say, I have a spring and a mass, and this mass is actually moving in air. So this is actually air which is blowing at uniform speed, u infinity, let us say, or u naught, whatever it will be. Now what will happen that in this particular system, so a complicated phenomena will take place because of the air flow. So what will happen? The air, if the air speed is small, then what will happen is that the air will flow this side, like this. The flow of air will be like this. And in this particular region, there will be certain separation. Okay, so this will be this is the region where there will be kind of a turbulence because it is not so smooth all the time, so it will get separated at one particular point. So there is a separation taking place. Now, if you increase the speed, then what is going to happen is that these vortices, so it will form in this region, actually, it will form vortex. Okay. This will form vortex. Now, what will happen that at a given certain speed, this vortices will actually gets detached. So, what becomes of this is that this one, there are vortices, okay, and one of the vortices get actually detached. So, because the air is blowing, so it carries air. This vortex actually now gets developed, is developing. This has got detached, and this is now a new vortex is actually generating because now air immediately when the vortex is separated, then the airflow will be entrained in this region, and another vortex will start forming. Meanwhile, what will happen? These vortex, so at certain time this vortex has gone here, so these vortex will be separated. Okay, and now so this vortex has now grown up bigger. Then there is no vortex, so this is now in the growing mode. Here, when it has grown bigger, then this gets detached, and then this becomes bigger, and so on. So this kind of series of vortices will be separated from this body. Okay, so these vortices are actually known as von Karman. Von Karman vortex string. So this actually series of vortices will develop in alternate times, so alternately. Now, as the vortices are developed, so what will happen? Vortices actually they are fluid masses which is having certain velocity, so it has certain momentum. As soon as they get detached, so the momentum of the system changes, and the fluid momentum imparts a force to the body. Okay. So what will happen because of the separation of vortices? Actually, what will happen? This mass will start oscillating. Now, at one point of time, what will happen? That this oscillation will be very large, and these vortex actually they will also they will not be like this, but there will be some other entrainment phenomena, some complex phenomena will take place, and the motion of the vortex will be also changed according to the motion of this bigger mass m. Okay, so this kind of oscillation actually what happens? There is no external excitation, but this gets excited because of the wind. Okay, the air. Air, of course, there it is energetically this mass and spring. It is a passive system, so it does not have its energy. It cannot exert energy on its own. It has a fixed energy. Okay. Now, for oscillation, like building up oscillation to a large excitation, it needs energy from outside. So it gets the energy from air. But this kind of excitation, this is actually developed because of a small initial motion. If there is a small initial motion here, then this motion will keep on building up. So it's kind of an unstable situation where the motion develops because due to its own dynamics. Okay, so it is unlike the other excited system where we apply force and then you get the resonance or high excitation, but large response. But here the large response is because of the motion of the small motion of the system itself. So this kind of excitation we call normally as self-excitation. So it gets excited itself. Now, self-excitation is actually a phenomena which comes under instability. So actually, this motion sometimes becomes unstable, and because of the instability, then the response goes up. Those who are attending automatic control, they will know more about this kind of instability problem in the physical systems. So instability happens because of various reasons, but all of this oscillations because of this kind of instability, we call it a self-excitation. Okay. So we have now chalked out 4 different types of excitation. One is the force excitation, displacement excitation, or the motion excitation, or parametric excitation, and self-excitation. Now, of these 2 we will consider in our course. For studying parametric excitation and the self-excitation, self-excitation happens only in the nonlinear system. There is no linear system where the self-excitation takes place. Parametric excitation can be in the linear system or nonlinear system, doesn't matter. But to get the response of a parametrically excited system, we need mathematical tools which are normally taught in the subject called the nonlinear vibration or the nonlinear oscillation. So this we'll learn in the nonlinear oscillation. If the force is deterministic, or random, so we'll consider this part. Random force or random displacement can be taught only in the random vibration course. So we'll now restrict ourselves to the excitation caused by the deterministic force and the deterministic motion. Parametric excitation, self-excitation, we will not consider in the class. So that is, we'll chalk out our restriction. Is this clear? Clear the way we classified the excitation, classified the system, etc.
Sir?
Any doubt?
Sir? Excuse me, sir. Excuse me, sir.
If I do not get, I can hear you.
Sir, so linear and non-linear oscillations will not be there in force excitation and motion excitation.
No. Linear and
Sir, actually your video is somewhat lagging, that's why.
linear and non-linear system is one way of classifying the system. Okay. Then the classifying the excitation. So this is the system. Okay. System can be linear, can be non-linear. And then classify the excitation. So this will be for force, this will be displacement or the motion. Then parametric and the self-excitation. What I say is that this self-excitation normally takes place for the nonlinear system. So we need to know the nonlinear model. But all this can be actually either for the linear or nonlinear. Linear or nonlinear, both can have this kind of excitation. But the self-excitation is actually exclusively for nonlinear system. Okay, that's what I said. So we'll consider linear system, we'll consider force excitation and the motion, and this is actually deterministic and random. So we'll consider only the deterministic part. So deterministically excited linear system will be our subject matter of study. Understood? We'll
Yes,
consider linear system only. Non-linear system will not touch in this course because it involves other kinds of mathematics, which and it's more or less approximate methods. All the methods are approximate methods. So if you are interested, you can take up nonlinear vibration as an elective subject further in the next semester. But for today, for this semester, will be content with the nonlinear systems only. Okay. Is this
Okay,
clear?
sir.
I
Okay,
did not
clear.
get your doubt. Is this doubt clear?
Yes, sir. Yes, sir.
Okay. Okay. Now let us see. Now I told earlier that is the. Suppose we have a linear system. So what is a linear system? I just mentioned earlier. Suppose we have a system which is actually shown kind of in schematic manner. Suppose this is the system. And I have input. Let us say U is the input to the system, Y is the output to the system. So if I give U1, suppose I get Y1. So Y1 is actually, I should say, Y1 is actually maybe function of X U1. Let me put this way, although it is not exactly correct, but just symbolically I am writing this. Of course, we can question the validity of this particular expression, but just for the sake of explanation, I'm saying that Y1, let us say, is a function of U1 only. Similarly, if you apply, so what it means that if you give U1, you will get response as Y1. Then if you give U2, you get response as Y2. So Y2 is a function of U2. So the system becomes linear only when, suppose now you change to A1 U1 plus A2 U2. Response will be Y will be equal to A1 F A1 U1 plus A2 F U2. That means A1 Y1 plus A2 Y2. So this is actually the principle of superposition. Physically, it means that if we apply two inputs separately and get the response, and if we apply the same two inputs, maybe scaled together, then the response will be the sum of the superposition of the individual responses. So that is the physical significance of a system, well, the principle of superposition. And for a linear system, the principle of superposition holds. So this is one test where we can very well verify whether the system is linear system or non-linear system. Fine. Okay. Now, how do we know, or what will be the properties of the equation of motion will be there for a linear system? So one thing is that all the equation of motion is okay. Because of the force, all the other terms will come from the expression of the Lagrangian, which is equal to T minus U. Okay, so all the expressions, other terms will come from the expression from the Lagrangian, which is the kinetic energy minus potential energy. Now, potential energy can be function, any arbitrary function of Q1, Q2 up to Qn. So this is a function of Q1, Q2, Qn. What will be the kinetic energy? Kinetic energy will be equal to half, as I said, Mi, Ri, or Vi dot I equal to 1 to capital N now, because this is the total the system consisting of capital in masses, so the kinetic energy, total kinetic energy will be the sum of the individual kinetic energies. Right? Now, VI will be dri dt, and dri dt is what? This is equal to d dt of r from ri. You know, the significance of the generalized coordinates is that Ri can be expressed, so ddt of Ri, which is a function of Q1, Q2, Qn. So Ri can be expressed uniquely in terms of the generalized coordinates. This was the significance, this was the meaning of the generalized coordinate, that all the displacement, all the position vectors can be expressed in a very unique fashion with the help of the generalized coordinates. Right? So if you consider that, then the velocity will be equal to just del Ri. Well, if the displacement excitation is given, suppose I give, in general, Ri will be a function of Q1, Q2, Qn, but sometimes also if you have displacement excitation, that means if you give a specific time variation to a position, so then R may be explicitly also a function of time. But this we are not considering. I will consider only the function. There is no displacement. The displacement excitation. That is the R's are only a function of this thing. Sometimes also the constant may take place. This we. I should say I should include this one. Let me include this one. Then this becomes actually dri dt, partial derivative with respect to time, and then the chain rule, that is dri dqj and dqj dt. Okay. So where j is equal to 1 to n. So this is the expression for di. Okay. Now I'll write this dqj dt as qj dot. Okay. Then this is just a notation. All right. Then what will happen to the expression for the kinetic energy? This part is clear. This is clear.
Yes, sir. Yes,
okay.
sir.
Yes, sir.
Now we write the kinetic energy part. So kinetic energy will be half mi vi dot vi. Okay, so this will be equal to half. So here, what will happen? This one, so mi. So let me consider this as, let us say, v naught vi naught t. This part, then I name it vi naught t. Vi naught, which is a function of time. It's just a derivative. Of course, it is a function of this, not only time, but it's also a function of Q1, Q2, all this stuff. So therefore, you can also write down Q and time. And there will be other terms, that is J, this plus del Ri, del Qj dot equal to 1 to n, and dot of this vi so dot. Okay. So now what will, and this is actually over I equal to 1 to capital N. Now what we'll have to do, I'll have to take the dot product. So in the dot product, what will happen, what will come is that vi naught t, vi naught dot vi naught term will come, which is actually a function of q, and so the first dot product the term will be vi naught dot vi naught. So this will be equal to half I equal to 1 to n mi, then vi naught dot vi naught is done. Then what will happen? Vi naught dot this part, okay, and then this
Sir,
dot, yeah.
So the vi dot is del vi by del t, right? Del ri by
Till arrive at del t. Yes, this is what I wrote as vi naught, just naming. Okay, so this is just a name, the symbol of this delta Ri by del t. Okay.
Sir,
So now what? Yeah, is this clear? I mean,
sir, how is VA is a function of Q also, sir?
Q, because Ri was what? Ri was a function of Q1, Q2, etc. And in
Yes, sir,
addition,
but we using chain rule we partially differentiated, no, sir. Then why you can?
no, partially differentiated, but we differentiate. See, Ri was a function of this okay. Ri is a function of Q1, Q2, Qn, and T. Okay.
Yes, sir.
Now,
Yes, sir.
if you want to take the time derivative, then what will be the total time derivative? Chain rule apply. So del Ri del Qi Q1 Q1 dot del Ri del Q2 dot del Ri del T, then del T dot, T dot, what is T dot? Del T by del T, which is equal to 1, right? So therefore del R, so this is what we are doing. This is the time is explicitly appearing here.
Yes, sir.
Isn't it? So in that way, if you take any example, this is a very simple differentiation. You can try any example with differentiation. For example, if you take function f equal to, let us say, sine theta, so let us say omega t, sine omega t. So if you chain rule, you know, but what I am saying that maybe maybe at sine q, let us say q. Okay. Then how do you differentiate this? Q is a function of t. Q is the generalized coordinate. Suppose this is so. Then the total differential will be dA dt sine qt. So this becomes actually function of q also. The first term.
Yes. Yes.
Right. So please check yourself. I mean, if you have any still problem further, then let me know. But otherwise, if you just do a few, carry out few examples, then it will be clear. The other part, this will be now J2 will come because these two dot products, first of all, Vi dot this and this dot Vi, so they will be same because dot products are commutative. So now it will be Qj, so Vi dot del Ri del Qj dot. Okay, so this will get second expression, and the third expression, this will be now what? This will be del Ri. Just to write it down in a different way, I'll have to take help of two variables, like two subscripts, the j and k. So del Qj and dot del Ri del Qk and Qj dot Qk dot. So this will be the expression, because I have written on only one subscript. This j is together, but j I can replace because this is summation. So q1 dot del Ri del q1 plus q2 dot del Ri del q2 and so on. So I compress this expression by writing a subscript like this, qj. Okay, so j, what I have to do when I take these two terms, because j is appearing twice here, so that need not be necessarily so, because I could have replaced this j by k, because this is just a notation, and this if I replace j by k, the summation remains same, right? So I have to expand the sum, and this will be remaining same if I could replace j by any other term like k. So when I take the dot product, I will have to explicitly write down this as two different subscripts. So therefore, del ri del qj dot del ri del q k dot k del qk and qj dot qk dot. Okay. So is this clear? Right?
Yes, sir.
So
Yes, sir.
now from this expression, what we see now is that T kinetic energy, there is a part which is quadratic with respect to qj dot, okay, the generalized velocities. So this quadratic term. So we'll have term like half, maybe I write down this as, let's say, aij, which is which are, because this is function of qj and qk, so therefore q and qj dot, qk dot, j and k together, right? Then this term plus, let us say, half will cancel out, so therefore this will be j bj, which may be a function of q, and that is qj dot, and the other term which does not depend upon this is c, which is a function of q. So this will be the general. I will not say c. I will write down t naught, okay, which is the function which does not depend upon qj dot. Okay, it depends on qj, but it does not depend upon qj dot. It can also depend it can also depend on r and t, and the general form of the kinetic energy will look like. It will be a quadratic function of qj's dots. Okay, so the generalized velocities will be actually at least one quadratic term will appear. So it is a, so this kind of expression we'll have for the t. The Lagrangian, then of course,
So the T naught comes from where? Vi dot.
vi dot, yes. So this actually does not depend upon, there is no qj dot.
Okay.
Okay. So T naught comes from here. So L will be equal to half this quantity. Okay, Aij qj dot qi dot, not j k, I and j. I dot j dot plus b j qj dot plus t naught minus q, which is which again, q is a function of, u is a function of qi, so therefore this entire thing is a function of q naught only, q only. Okay, so this is the Lagrange expression, Lagrangian, right? Now if you take del L del qi dot, so qi dot, then one term will come from here, isn't it? So this will be, so there will be some term which is, okay, there will be a function, maybe I'll write down this way, aji, right, aij qj dot, so there is the linear term. If you take the partial derivative, then this will be bj, right? There is no contribution from this term because these are all function of q. If I take the partial derivative with respect to q dot, I'll get qi ij equal to 1 to 2. Right? So this is what we'll get, and del L del qi, del L del qi, you'll get from all these expressions, because these are all functions of qi, so therefore derivative of all these terms will appear in this particular form. Okay. So now we can write down the equation. This part is clear. I mean, it's only I have not done it this thing, but this becomes actually, you see that this becomes half del aij del Okay, I have considered, yes, del K, let us say del Qk and Qi dot, Qj dot. I'm not writing down this because it will be a little lengthy expression and we do not require this part. So I'm not carrying out this expression and the differentiation explicitly in this particular form. So what I want is that this now our equation of motion at least will be, the first part will be ddt of this thing, that is a ij qj dot plus bi j equal to 1 to n and minus del L del Qi. This is equal to, let us say, Qi. Okay. Now, in general, now what you have, if you take the differentiation, if you differentiate it, so one differentiation will be like this: Aij Qj double dot plus Qj double dot plus, let us say, here these are all functions of Qi, so therefore del Bi, del T, del Qj, del Bi, del Qj, then Qj dot, chain rule, etc. will appear. But what we'll see, and then here also del Aij, del Qk, Qk dot, Qj dot, all these terms will be appearing. Now, there will be other terms which I am not writing, but what is very important to note is that this term, the first term here, this actually involves the second derivative, and that is the acceleration term. So in general, the equation of motion will have this Aij, which is Qj double dot, j equal to 1 to n, plus all these terms which will be either, so Fi, which is a function of either Qj, Qj dot, so Q dot and Q. So all these terms. So Q and Q dot, maybe the time also will appear, and this is Qi. So this will be the general form of the equation. Okay. And Aij's are also maybe function of coordinates Qi. Now, when we have to have this linear equation, then what we need here, this must be for the linear equation. Now, in general, this is a function of q's, but for the linear equation, linear system, what will happen is that this here, so this term Aij must be constant, or at most function of time only. Fi, this will be actually two parts. One will be in Qi plus Qi dot. So otherwise the equation will be non-linear. So this is a constant quantity. Let us say lambda 1 and this is lambda 2. Okay, Fi will be this form only for linear system. So for the function, this will be equation will be Qaij Qj dot double dot plus all these terms. Now that will be the equation of motion in general. So if you get the equation of motion, then it will be in this form: Aij, then Qj double dot, j equal to 1 to n, plus this term, this one, this not, I wrote this one, maybe what I should have written down, Fi will be Bij Qj plus Cij Qj dot. Okay. So here it will be Cij, or let us say Bij Qj plus Cij Qj dot. This is equal to Qi. So this will be the general form of the equation of motion, because this is only linear. So I have excluded all the nonlinear. Anything other than that will lead to the nonlinear equation. So the linear equation, just like this here, all the generalized accelerations will be there. Similarly, in this particular term, which could be a one very lengthy expression. I do not have to consider that. But what I know that if this has to be linear equation, then this expression Fi has to be of this particular form. Otherwise, it will be nonlinear. So this is the general form in which this Fi can be expressed so that the system becomes linear. So this will be, in general, the equation of motion of a general kind of linear system. Okay, Qj. Okay, and this will come. This I will not prove. You can check. This will come if the Lagrangian actually becomes Lagrangian. This becomes a homogeneous quadratic function of Qi and Qi dots. So if this becomes like this, half Aij Qj dot Ui dot Qj dot I and j, this plus this becomes, let us say, what becomes of this? So this becomes Bij. Okay, so this will become Cij Qj dot. Okay. So let us say Cij Qj dot Qi Qj dot. Okay, and this may be half, this may not be half, plus Bij Qj Q Qi Qj on stuff. So this is actually an expression where this may be half, half Bij Ui Qj. So this is the expression where we have these are all constant quantities. These are all constants. So now this is actually a homogeneous quadratic equation in terms of Qi and Qi dot. Okay. Now, if this is the homogeneous quadratic equation, I can check that this del L del Qi dot, del L del Qi dot, this will be equal to, what will be that? This will be Aij Qj dot plus Cji Qi here. Okay, and del L del Qi, this will be equal to Cij Qj dot. Okay, Cij Qj dot plus this will be equal to Bij Qj. So this will be this one, the del L del Qi on the stuff, and these are constant quantities. I wrote, now here I wrote this carefully, be careful here, Cij Qi Qj dot. When I differentiate it with respect to Qj dot or Qi dot, I should say this is J. This is Qi and Qj. So what I did, I say Cij, I changed to Cji. This comes because of the particular way to differentiate this kind of expression. So you think over it. If you do not understand this particular mathematics, I can explain again the next class. But when I differentiate with respect to Qj dot, this becomes actually Cji Qj and Cji, not Cij. Here, but when I differentiate this with respect to Qi, then this becomes Cij Qj dot only. Okay. So this change in the suffix is quite important. You have to note it carefully. Bij and this is Qj. I assume that Aij and Bji, these are actually symmetric. So I assumed here that Aij equal to Aji and Bij equal to Bji. So that is the assumption involved, which is of course almost true, and which you have seen that. Which you see from the expression, you'll be clear that this is so. So Ai and A and B, these are actually, you can say that these are the elements of a symmetric matrix. C, J, I did not consider anything. So if we have this part, then the equation of motion, what will be the equation of motion? Equation of motion will be now derivative of this part, so therefore Aij Qj double dot time derivative, this plus Cji Qj dot plus Cij Ci minus Cij Qi. So therefore Cij Qj dot, okay, plus or minus Bij Qj. This is equal to Qi. So that will be the equation. Okay. And you see that except for this definition of Cij, which I took otherwise, but so this becomes actually a linear differential equation and a couple differential equations, couple linear differential equations. This is becoming a little mathematical, but I will come to simple expressions when we start with the singular degree of freedom system. But what I want to say is that this generalized, the linear equation will come automatically if you consider the Lagrangian to be generalized quadratic equation. So if it is a quadratic equation in Qa and Qj, then only then you will get the linear system of equations. Now that is important because we know that here, for example, I have this pendulum here. So what I know is that this equation of motion, see, the kinetic energy will be equal to, L will be equal to half ml square theta dot square, if you consider this theta dot square, minus of that, so therefore mgl cosine theta, minus cosine theta, minus mgl cosine theta, because if I consider this as our reference point, so therefore this distance will be equal to L cosine theta. So minus mgl cosine theta, and Lagrangian is kinetic energy minus potential energy. So this becomes equal to plus mgl cosine theta. Fine. So this is like that. Now this equation, I know that this Lagrangian will definitely lead to a nonlinear equation, because what? Cosine theta is actually not in the quadratic form. So if I write down cosine theta, so 1 minus theta square by 2 plus theta to the power 4 by 4 factorial and so on, because of the presence of these terms, theta to the power 4 and higher order terms, this becomes nonlinear. So to linearize this equation, what we'll have to do, we'll have to so linearization will be possible when this term is neglected. That means if you consider Lagrangian to be half ml square theta dot square plus mgl 1 minus theta square by 2, then it becomes actually a differential, a quadratic expression in terms of theta and theta dot. And if you write down the equation of motion, you will get this equation of motion as ml square theta double dot plus mg L theta dot equal to 0. So theta double dot plus g by L theta equal to 0. So that will be the linear equation of motion. This linearization, so we can either linearize, so what we can do, we can get the equation of motion, then we can linearize, or at the beginning we can linearize the Lagrangian, and then also we'll get the same set of linear differential equations. So linear differential equation will be possible when the Lagrangian has only quadratic term and not more than quadratic term. So this is the important thing which you remember. The equations of motion will be linear when the Lagrangian is quadratic in Qj and Qj dot. Is the message clear? I mean, the derivation was a little bit complicated, but what finally came out to be a very simple thing, that is, the system can be linear only if the Lagrangian is quadratic in generalized velocities and generalized coordinate. Is this clear to you?
Yes, sir.
Yes, sir.
Okay, good. So, so, uh, so here, for example, suppose the pendulum, let us say, I'll consider one more thing. Suppose this is the same pendulum I take, and the equation of motion becomes theta double dot plus g by L sine theta equal to 0. Okay. Now there are certain positions where theta dot will be 0, and at, let us say, theta 0, theta dot equal to 0. That means if you and you could maintain the velocity equal 0, that means what I have to do, I go to this position theta 0, I do not apply any velocity, I do not give any excitation, so the acceleration will be 0. That means the velocity will not change. That means it will remain there forever. Okay. So these particular positions, these are called the equilibrium position. So theta naught, if this condition is satisfied, these are called equilibrium position. Equilibrium position. So here in this case, suppose we want to find out this equilibrium position. What will be the equilibrium position? So what I have to put? So theta double dot will be 0. Theta dot is not there. So g by L sine theta dot equal to 0. So this is the equilibrium position for this physical pendulum, for this mathematical pendulum here. Okay. Now g. So this means that theta naught can have two values, 0 and pi. 0 and pi. Okay. There are two values for which this is equal to 0. That means if you keep the pendulum here, if you do not disturb the pendulum from this point, then the pendulum will remain there forever. That is that our experience shows that, and intuitively also we understand that this has to be so, because the earth is pulling it all the time vertically downwards. So there is no, if there is no motion given to this pendulum, then it will remain there forever. Theta equal to 0 is an equilibrium position, and that is very pretty obvious. What it says that this one, if the pendulum is kept here, then also the equilibrium is maintained. First of all, what we need is that the string will not do. Earlier case, actually, we had a string connected to the mast, and this was hanging down, so therefore the string was under tension. So it was possible to maintain the equilibrium. But now, with a simple string, it will not do, because the string cannot take any compressive load, so it will fall down. If you have a massless rod hinged here, okay, a thin rod which is connected here, and if you put the mass upward, then our equation says that this will be an equilibrium position. That is, if you do not disturb, then it will remain there forever. But this is not so obvious, because we do not, our experience actually tells us otherwise. So it can never stay here forever. That is the reason, is that although we are not disturbing it anything consciously, but because of the presence of air and so always small disturbances are there, and because of this disturbance, this actually is falling down. Why it is falling down? Because this equilibrium position is different from the other equilibrium position. Okay, so what will happen that, so this is one equilibrium position, this is another equilibrium position. If you keep this in vacuum, if you do not allow the base to move at all, then you can maintain this equilibrium position. In the control systems, we study sometimes this problem, that is how to stabilize this equilibrium position. Normally it is unstable equilibrium position. If you know, if you just give it small tilt or if you disturb, it will fall down. So it cannot stabilize there. But we can make it stable by applying certain control signal. So, for example, it's a child's game to actually keep the keep this particular body erect by applying base excitation. So I can, if it's a long stick, then I just maneuvering our base, I can keep it very vertical. I can try, and then it may be possible if it's a longer stick. So this is actually equilibrium position, which is unstable in general sense, but we can make it stable. But nevertheless, this is an equilibrium position. Now, what we'll have to
Sir,
do? Yeah.
sir, did you also write theta dot is 0?
Theta dot is 0, but theta dot is not appearing in the equation.
Sir, but for like this pendulum, it will
Yeah.
it may have theta double dot 0, but not theta dot 0.
Where? Here.
Yeah.
So theta dot, say theta dot is our initial value. Okay, theta dot is the initial value. At time equal to 0, suppose what I say, what I let me write down. So let at time t equal to 0, theta equal to theta 0 and theta dot equal to 0. So this is our initial condition. This I can always specify. Right? This is the initial conditions, it's our choice.
Yes.
What I say is that if theta is equal to 0, then this implies that theta will be theta 0 for all time. That means for all time theta dot will be 0. That is, definitely that means that theta double dot is 0, because if the velocity is 0 over an interval, then the acceleration is always 0. So what it means that those are the particular equilibrium position where you keep this body initially with 0 velocity, it will remain there forever without any velocity. Okay, that is what that is what that. Well, you're right that it can have velocity without acceleration, but what I meant is this one. At initial time, if I keep the velocity 0 and at position theta naught, then it remains there forever. So this is the definition of the equilibrium position. All right. Now we can. So now what we do?
Sir,
Yeah.
sir, like how is it different from like releasing a ball at an angle theta naught?
Releasing a ball at a,
Like the same ball and the string. Like if we release it at an angle theta naught, then also like the velocity will be 0, initial velocity, but there is some acceleration.
No. Okay. So what you want to say is that at theta naught, say it again, please.
Sir, like the same condition, like if at equal to 0, theta equal to theta naught, like if you just release it, then also like the velocity will be 0.
So that is releasing. So I keep it here and release it.
No. At an angle theta naught, sir, like let us say some 60 degree or something, and then you release.
So
like
this angle, see this angle, actually it is not arbitrary. There are, so equilibrium position cannot be arbitrary. So again, let me explain. So this is the equation mg g theta double dot plus g by L sin theta equal to 0. So I am looking for, in general, what you see, if you have at time t equal to 0, theta equal to theta naught, and theta dot equal to 0, I cannot say that theta will be always remaining at theta naught. If I take this pendulum here at arbitrary position, let us say theta naught here, I leave, and then it will oscillate. So it cannot have, theta cannot remain in theta naught, and theta dot also does not remain 0 all the time. And
it is not vice versa, right? Like two-way, only one way it is correct. Like at equilibrium, t equal to 0, theta is theta naught, theta naught equal to 0.
I'm looking for special values of theta naught, not all arbitrarily, but I am finding out what are those theta naughts. So my question is, what are those theta naught for which the following conditions hold? And what are the conditions? At given at time t equal to 0, theta equal to theta naught equal to 0, we get theta equal to for all time so that is what my question is. That is, I want to find out those values of theta naught for which this condition is satisfied. So any arbitrary theta naught will give you this. If you consider any, for example, here for this case, if I take any arbitrary value, let us say 30 degree, if you release for 30 degree, then this will oscillate. Theta t will no longer be theta naught all the time. Theta naught will no longer be 30 degree. Sometimes, maybe at some, you understand that periodically it comes to this position, and theta dot becomes 0, but it does not remain there permanently. So definitely it is not equilibrium position. Equilibrium positions I have to find out. So this condition, this answer, the answer to these questions I have to find out. Okay, and then I will call this as the equilibrium position. So for example, this one, what I impose here is that I impose that means what? That means theta naught will be 0. So I want to find out theta naught. So those theta naughts I am finding out. So what will have? So G by L sine theta naught, those theta naught, and then this one, the theta naught, this is equal to 0 because for that there will be no acceleration. The mass is not going to move. And then I have to solve this equation, G by L sine theta naught equal to 0. Solution to these equations will give us the equilibrium values. Okay, solution to this will give us the equilibrium values. And so this is not any arbitrary angles, but only the theta naught equal to 0 or pi. These two will be only the equilibrium positions where this condition will be satisfied. That is, if you keep this motion, keep the body initially here at rest, it will remain there at rest. What this one is saying, and mathematics is saying, is that this configuration is also actually one equilibrium configuration. That is, if you keep it here, do not disturb, then it will remain there forever. But this does not appear because there is a very fundamental difference between these two. And this difference will be clear if you linearize this equation. That means what I do, these are the equilibrium position. I want to find out what will happen if the angle actually changes by very small amount with respect to this theta naught. So what I say is that theta, I consider theta naught plus certain value eta. So this is our small angle where eta is very, very small compared to 1. So this is I actually finding out the motion around the equilibrium position. So this is what we are doing, finding out motion around the equilibrium position. Okay, motion around the equilibrium position. So here the equation, so theta double dot will be equal to eta double dot, and sine theta will be approximately equal to what will be sine theta. So this is equal to sine theta naught plus eta, and this will be equal to sine theta naught into cosine theta plus cosine theta naught into sine eta. If eta is very small, then this becomes sine theta naught into 1. I'm excluding all the terms which are higher order than eta. So theta naught into eta. So this is what we have. Sine theta is approximated this way. Now our equation now around the equilibrium position, this will be equal to theta double dot plus G by L sine theta is equal to sine theta naught plus cosine theta naught times sine. Right. Now when theta naught equal to 0, you very well see that this term will disappear. This will be equal to 1. So then equation of motion will be G by L eta equal to 0. And when theta naught equal to pi, then this will be minus G by L theta. So there is a fundamental difference between these two equations. Here we have a positive coefficient and this is negative coefficient. And what the solution will show that this kind of solution, this kind of equation will give you harmonic oscillation, but this will give you actually an exponential increase. That means given a smaller displacement from this equilibrium position, it will diverge. That means it will always go away from the equilibrium position, and that's what we see. That is, if you disturb a little bit, then it never comes back. So this equilibrium is kind of a stable equilibrium. This is actually unstable equilibrium. So oscillation takes place about the stable equilibrium position. So one way to linearize this is that first two ways you can linearize. Either you take the kinetic and the Lagrangian as quadratic function in this one, or you can get the complete nonlinear equation. So what I say is this one, that is the techniques to get linear equation. So I get linear equations either by writing down the Lagrangian function as quadratic in Qi dot and Qi initially, and then derive the equation of motion, or first find out the nonlinear equation, then find out the equilibrium position, and then find out the linearization. So this is technique called linearization. Now this linearization, this method is actually a shear shot method, but here if you want to use this kind of technique, that first you consider the quadratic equation, and then you have to be careful, because sometimes you may miss certain equilibrium positions, so therefore this getting quadratic equation may not be always so perfect, because this quadratic equation has to be obtained around the equilibrium position. So equilibrium position we need to know, but this technique does not presuppose any idea about notion of the equilibrium position. It derives the nonlinear equation, then find out the equilibrium position, and then linearize account the equilibrium position. Linearization means that we take the value of the generalized coordinate very near to the equilibrium position, and then put this in equation of motion and neglect all the nonlinear, that is the higher order terms. Okay, retain only the linear terms in the equation of motion. So these are the two ways of deriving the linear equation. This is very important because from next class onwards, we'll not look at how to derive this equation and other things. We'll straight away take the linear equation. First we start with a very simple, the simplest form of the linear equation of the harmonic oscillation, and then discuss its properties in details. After that, we'll go to more degrees of freedom, okay, multi-degrees of freedom system. So these are two ways, and I hope you have understood at least about the idea of how the things are done. Is there any doubt? Anything you want to know?
No, sir.
Okay, good. Then what we'll take, I will take a short break for 2-3 minutes, and we'll come back. We'll discuss certain problems. Okay, I'll give you some problems. We'll solve them together. Fine. Just let me take a break for 2 or 3 minutes. Okay.